Epimorphisms, which is in the main building, which you haven't seen yet unless you're familiar with it. So we'll go together after the main session, sorry, the plenary session now. So please, whenever you have Puteano on the booklet, that's not true anymore. Whenever you read Puteano, that means Aula degli Stemmi, which is in the main building. You'll get familiar with it very, very quickly. And as a consequence of this, coffee breaks will also change location. And the new location is nearby the Aula degli Stemmi. So it's going to be in the Palazzo della Carovana, 3rd floor. You'll find us pointing into the right direction. So we apologize for this. It turns out that half of the information provided here is wrong. Still, it's not useless. Please just rename Puteano with Aula degli Stemmi, which, by the way, is actually our most representative lecture room in the whole of the Scuola Normale. So it's not, after all, you're not worse off in this change. Okay, so that's that, and my watch is now saying that I should introduce our next plenary speaker, and it's really my big pleasure to do so, to introduce Jon Williamson. Jon is Professor of Reasoning, Inference and Scientific Method at the University of Kent in Canterbury, and he's also Director of the Centre of Reasoning, also at the University of Kent. So it's a big pleasure for us to have him here, and he, as you can see, is going to talk about inductive logic for automated decision making. So, welcome, Jon.
It's a great pleasure to come, and lovely to visit Pisa once again. Let me just sort this out.
Probably better off if you put it up.
Can everyone hear me okay?
It moves less.
Is that okay? Yeah? Good. Okay, so the task of this talk is really to advertise inductive logic to you. Inductive logic was an area of logic that sort of boomed from the 1950s to the late 70s, early 80s, and then went out of fashion rather suddenly, but for all the wrong reasons, I think. So I'm going to try and explain why there's still life in inductive logic and why it's of interest and useful to you. Oh. Is that better?
There's a feedback problem, so if you try and stick as much as you can, I'm sorry, John.
Okay.
That should be
okay. I'll stick here. Good. So first of all, why should we be interested in inductive logic? Well, the reason is that in order to make decisions, we need inductive logic. So decision making requires inductive logic. So here's an example of a decision problem where you might have an automated decision support system helping a clinician with medical prognosis and medical treatment situation. So suppose that there's a patient who's had cancer, had some treatment, and the consultant's trying to decide whether to give further treatment. Which further treatment to give? Chemotherapy or radiotherapy, for example, quite a common problem. Largely, the treatment that will be given will depend on how likely the clinician thinks that the cancer will recur in the absence of any treatment. So here R stands for recurrence.
Sorry, can you turn it off? Turn on the stage. Thank you.
I'm sorry.
That's on, I think. Okay. So R stands for recurrence, and here we've got a decision table which specifies the utility of the relative treatments according to whether the cancer would recur or not recur. So chemotherapy has got high positive utility if the cancer would recur, but fairly large negative utility if the cancer wouldn't recur, because the side effects of chemotherapy are typically harsher than those of radiotherapy, for example. So that's how to read the values in this table. And then Bayesian decision theory says you should choose the treatment that maximizes expected utility. So you multiply each utility by the relevant probability, so 5 times the probability of recurrence minus 3 times probability of no recurrence. That's the expected utility of chemotherapy. Here, 4 times the probability of recurrence minus 1 times the probability of no recurrence. That's the expected utility of radiotherapy. So you give chemotherapy if the expected utility of giving chemotherapy is greater than that of giving radiotherapy. Collecting the terms, if the probability of recurrence is greater than 2/3. So this is a typical sort of decision problem you might have in a medical situation. The question, of course, is how do we determine the probability of recurrence? There's going to be some available evidence, general statistical evidence. It might give that the probability of recurrence given metastasis is 0.7, for example. Probability of recurrence given the presence of some biological marker is 0.4. And there might be some symptoms relevant to the patient, so that the cancer is metastatized, that the biological marker is indeed present. So you've got some evidence here, and you want to determine the probability of recurrence to see if it's high enough to trigger a particular action, a particular decision. This is really just a question of inductive logic. So you've got some premises on the left-hand side of the turnstile, and you want to know what probability to attach to a proposition on the right-hand side of the turnstile. So to what extent do these premises imply some conclusion proposition? So the general point is this: if you want to do decision making properly, you need some theory of inductive logic, because decision making requires ascertaining some probabilities. In general, you won't have them just given on a plate to you. You'll have to derive them from other evidence. And inductive logic is the logic of which probabilities to attach to a conclusion given some premise statements. And so this led I.J. Good very early on, 1950, to say something like Carnap's theory of inductive logic would be required if an electronic reasoning machine is ever built. So very early in the days of AI, it was recognized that you would need inductive logic if you're going to build useful systems for reasoning and decision making. So that's why we should be interested in inductive logic. I'm going to talk next about what I call classical inductive logic, which is a very simple approach, easy to see how it works. Unfortunately, it's not entirely effective, and it suffers from a problem of learning from experience, which I'll talk about afterwards. So classical inductive logic is a good intro to inductive logic, but it doesn't entirely work. And then I'm going to present a new approach to inductive logic based on some philosophical work in epistemology. And I'll try and show how it succeeds where the classical approach to inductive logic fails. And then hopefully I'll have time to talk a bit about inference in inductive logic. Okay, so classical inductive logic, we've got an argument here. A implies B, B therefore A. In classical deductive logic, we ask whether this is a valid inference, and we know it's not because we can build a truth table for the inference and find a line of the truth table at which the premises are true but the conclusion is false. So that's how we know it's not a valid deductive inference. In inductive logic, we're not interested in deductive validity. We're interested in related notions. Partial entailment is a key concept in inductive logic. To what extent is the conclusion plausible given the premises? So what level of plausibility y should you attach to the conclusion given the premises? That's a question of absolute entailment, but there's also a relative question as well. Suppose y attaches to the conclusion in the presence of the premises and z attaches to the conclusion in the absence of any premises. Is y any bigger than z? If so, the premises support the conclusion. If y is smaller than z, then the premises would disconfirm the conclusion. So this is a question of relative support in the presence and absence of one or more premises. Okay, so classical inductive logic is very simple. It answers the question of partial entailment by building on the truth table method that we use in classical deductive logic, propositional logic. So the approach here is that the degree of partial entailment is just the proportion of those truth assignments that make the premises true that also make the conclusion true. So in the argument that we were looking at, we've got two truth assignments, the first and the third line of the truth table, that make the premises true. One of those makes the conclusion true, so degree of partial entailment is just a half under this approach. And this approach to inductive logic was introduced by Wittgenstein in the Tractatus at the same time as introducing the truth table method. It follows very naturally from a key interpretation of probability, what's called the classical interpretation of probability. And Laplace puts the classical interpretation very nicely like this. He says, the theory of chance consists in reducing all the events of the same kind to a certain number of cases equally possible. That is to say, to such as we may be equally undecided about in regard to their existence. So here, there's two equally possible cases, the first and the third line of the truth table. These are both compatible with the premises. And in determining the number of these cases favourable to the event whose probability is sought. So one of these two cases is favourable to A here. The ratio of this number to that of all the cases possible is the measure of this probability, which is thus simply a fraction whose numerator is the number of favourable cases and whose denominator is the number of all cases possible. Okay, so we just take a simple ratio. And the germ of the idea is already present in the 18th and 19th century in the classical interpretation of probability. So let's look what happens when we don't have any premises. Here we've just got the conclusion A. This is true in half the lines of the truth table. So in the absence of any premises, probability a half attaches to the conclusion still. So remember we had this question of support. Take the degree of partial entailment in the presence of the premises, subtract the degree of partial entailment in the absence of the premises and see what the difference is. Here you've got 0 degree of support. So not only is this a lousy argument from the point of view of deductive logic, it's also a poor argument from the point of view of inductive logic as well, affirming the consequent, because the premises don't raise the degree of partial entailment of the conclusion. You can ask other related questions. Suppose we hold one premise fixed, A implies B. Then we have the following probability table. A is true on 1/3 of the possible truth assignments, so 1 out of 3 lines of the truth table that make the premise true. So in the presence of A implies B, A has probability 1/3. What this means is if you hold A implies B fixed and just come to learn B, then this raises the degree of partial entailment by 1/6. So you do have some inductive support if you come to learn B but holding A implies B fixed. And this question, degree of support in this case, is a question that Polya asked, and he argued that in this case any system of inductive logic ought to give you some positive support. If you hold A implies B fixed and come to learn B, then that does provide some support for A. So classical inductive logic validates this inference form of Polya's. Here's another example, got a different inference here. Exactly the same approach, you just build the truth table. Now we've got 3 propositional variables. 3 lines make the premises true, 2 of those make the conclusion true, so degree of partial entailment is 2/3 here. In the absence of any premises, half the lines of the truth table make the conclusion true, so degree of support is 1/6 here. Okay. There are actually, you don't have to take the difference here. There are a large number of different approaches to measuring relative degree of support, but it won't matter to us here which approach we use. So that's classical inductive logic. Let's look at why classical inductive logic isn't entirely satisfactory. Well, Carnap argued early on in his work on inductive logic that this sort of approach to inductive logic fails to capture the phenomenon of learning from experience. So in this example, we're examining ravens. This is the typical philosopher's example for testing inductions. Examining ravens and trying to work out whether the 101st raven we examine will be black or not. Now, in the absence of any evidence, we're going to attach probability 1/2 to the 101st raven being black. Got a very simple truth table here. Half the lines of the truth table make it true, half make it false. That seems reasonable. So in the absence of any evidence, it seems a reasonable conclusion to draw. But if we apply the same method in the presence of a great deal of positive evidence, so we've observed 100 ravens and found them all to be black, then classical inductive logic still attaches probability 1/2 to the conclusion that the 101st raven will be black. So we build our truth table. We've got 2 to the power of 101 lines in this truth table, only one of which makes the conclusion and premises true out of 2 lines that make the premises true. So degree of support is 0. Learning that 100 ravens are all black provides no support for the 101st raven being black. And this represents an inability to learn from experience. So Carnap argued that this inductive logic should be rejected because we can't account for learning from experience in this inductive logic. Actually, Boole had made the same observation sometime previously, and Wittgenstein had pointed out that the problem here is that you're treating the propositions as logically independent. So from the point of view of propositional logic, you're treating all these observations as different propositional variables, and that no connection between them can be picked up by the truth table method. The upshot is that an inductive logic needs to capture 2 phenomena. First, what I'm going to call inductive entailment, which is learning from experience. So this is the degree to which an observed sample of ravens makes it plausible that the next raven is black. So this is an ampliative concept. The propositions can be logically independent here, but still you can have positive partial entailment. Classical inductive logic, we've seen, fails to capture this concept. And this led Carnap on his program for inductive logic. So he devised a continuum of inductive methods, as they're called, which are trying to capture inductive entailment. So he abandoned classical entailment to try and capture learning from experience. On the other hand, we also need to capture what I'm calling logical entailment. This is the degree to which one proposition that overlaps another, so has logical structure in common, makes plausible the latter proposition. So for example, A or B provides some support for A because there's a propositional variable in common here. And this is attributable to overlap in logical form, logical structure. And arguably, if you want to capture this concept of entailment, you need classical inductive logic. This was the point made by Wittgenstein, that classical inductive logic does capture partial entailment that's due to overlapping logical structure between propositions. This led other researchers, in particular Kemeny and Oppenheim, to focus on classical partial entailment, so to research this notion of partial entailment, to try and capture logical entailment, but recognizing that they wouldn't be able to capture learning from experience at the same time. So round about the late 40s, early 50s, the field forked, if you like. The main program was Carnap's, which was focused on inductive entailment, but others were interested in capturing logical entailment. So this fork moved away from classical inductive logic, and this fork carried on developing classical inductive logic. Wesley Salmon argued that you've really got a proper dilemma here. You can only capture one notion of entailment at the expense of capturing the other notion of entailment. And there's not going to be an inductive logic that successfully captures both notions of entailment. So he says, if degree of confirmation is to be identified with what I call logical entailment, then classical inductive logic is the proper confirmation function after all. For it yields the result that P is probabilistically irrelevant to Q whenever P and Q are completely independent and there is no partial logical entailment between them. Unfortunately for induction, statements strictly about the future, so the next raven, are completely independent of statements strictly about the past, the 100 ravens already observed. Not only are they deductively independent of each other, but they also fail to exhibit any partial logical entailment. The force of Hume's insight that the future is logically independent of the past is very great indeed. It rules out both full entailment and logical entailment. If logical entailment were the fundamental concept of inductive logic, then it would in fact be impossible to learn from experience. So Salmon is trying to say here that if you want to capture this concept, you need classical inductive logic, but then you fail to capture this concept. So it's looking impossible to develop a notion of inductive logic that can capture both concepts at once. Okay, so now I'm going to introduce a more recent approach to inductive logic that I claim can capture these two apparently conflicting notions of partial entailment. And I'll try and explain how it can capture them. So this is an approach based on Bayesian epistemology, in particular objective Bayesian epistemology. So I'll just explain first what this philosophical theory is, and then we'll see how it applies to inductive logic. So Bayesian epistemology is a theory of strength of belief, and it says that you should apportion the strengths of your beliefs according to three norms. So first of all, strengths of your beliefs should be representable by some probability function, P sub E, some function in the set of all probability functions. That's the first norm. The second norm is if you know something about the chance, objective or physical probabilities if you like, then your degrees of belief should be calibrated to those physical probabilities about which you've got some knowledge. So in particular, if you know that the chance function lies in some set P star of probability functions, then your personal probability function, your belief function, should also lie in that set. Well, actually in the convex hull of that set of functions. So this is sometimes called a calibration norm. Another version of this norm is called the principal principle in philosophy. So your belief function should be calibrated to your to the chance functions that are compatible with your evidence. So that's the key way in which evidence constrains degree of belief. A belief function is not going to be uniquely picked out by the calibration norm and the probability norm. And in the absence of constraints, further constraints on your degrees of belief, they should be as equivocal as possible. So you should give each basic possibility as close to the same degree of belief as you can. You should be equivocal over the basic possibilities that are compatible with your evidence. And usually, following some work of Jaynes in the 1950s, this is typically cashed out using the maximum entropy principle. You should adopt a probability function that's well calibrated, that has maximal entropy, where the entropy of a probability function measures the amount of uncertainty embodied in the probability function, or the degree to which the function equivocates. So objective Bayesian epistemology says you should apply these three norms to determine your belief function. It differs from subjective Bayesian epistemology in the following way. So subjectivists would say just one norm is necessary and sufficient for rationality here. Your belief function should be a probability function, and it's up to you, entirely up to you, which function you choose. Any function would be rational in this situation. Then the subjectivist would say, well, you need a separate norm that governs how you update your degrees of belief. So if you learn a new item of evidence, you need to update your degrees of belief in a certain way. The objectivist says, if you learn new evidence, you just apply these three norms all over again. So you don't need a separate updating rule for changes in degree of belief. So that's broadly the difference between the subjective approach and the objective approach, which buys these three norms. And typically these are justified using betting considerations. So there's a so-called Dutch book argument that's used to justify the probability norm. This says that you should adopt the probability norm, otherwise you can be forced to lose money whatever happens. You should abide by the calibration norm, otherwise you can be forced to lose money in the long run if you bet on the same sort of situation over and over again, and you don't bet according to the chances, then a bookie can exploit that to force you to lose money in the long run. And then there are arguments that appeal to scoring rules, which are rules that are used to evaluate weather forecasters and so on, that say that you should abide by the equivocation rule. Something I've been working on recently with Jürgen Landes is coming up with an integrated justification that justifies objective Bayesianism, these three norms all at once. And the sort of justification we apply here is that you should abide by these norms if you want to minimize worst case expected loss. So if you care about worst case expected loss, then you should abide by these laws. Okay, so that's objective Bayesian epistemology. Let's apply that to inductive logic. Well, the application is quite straightforward. Suppose you've got premise propositions phi 1 to phi k with various probabilities or sets of probabilities attached x1 to xk, and you're wondering what probability to attach to the conclusion. You say that the premises partially entail this conclusion if the probability of psi is in the set y of probabilities. So probability here is your rational belief function. If you ought to believe psi to some degree in y, where you take the left-hand side of the entailment relation as facts about chances, so statements about physical probability that's determined by your evidence, so constraints involving physical probabilities. So the objective Bayesian would say here that you need to choose a maximal entropy function P from within the whole set of functions that satisfy the chance constraint. So these are the functions that are constrained, that are calibrated with your chance information. So the left-hand side of an inductive entailment relation is interpreted as facts about chances, right-hand side as saying something about rational degree of belief. If you know this, you ought to believe psi to some degree in y. Okay, so first of all we're going to look at logical entailment. So the claim was that this sort of approach to inductive logic can capture the two apparently rather irreconcilable concepts of logical entailment and inductive entailment. First, we're going to see how the objective Bayesian approach captures logical entailment. Broadly, it does this because it can be viewed as an extension of classical inductive logic. So the probability norm says that you measure inductive plausibility by probability. And what this means is you can augment your truth table by a probability that attaches to each line of the truth table. The calibration norm says that these probabilities should fit the premises. That means if one of the premises turns out false, in particular, you should give probability 0 to that line of the truth table. Then the equivocation norm says that to the extent that your premises fail to distinguish between two possible assignments, you should be as equivocal as possible, i.e. give them as close as possible to the same probability, same degree of belief. So we've got two remaining lines. We give them each probability a half. And then you add up the probabilities for those lines at which the conclusion is true, the first two lines, and you get probability a half attaching to the conclusion. So the reasoning is rather different from the Wittgenstein's approach to classical inductive logic. But in general, it is true that whatever conclusion you would have got by classical inductive logic, you'll get the same conclusion by applying objective Bayesian inductive logic here. So objective Bayesian inductive logic preserves classical inductive logic and the truth table method in particular. So it captures logical entailment. The situation with inductive entailment is a bit more complicated, and we'll go through an example in a bit of detail to explain how objective Bayesian inductive logic captures inductive entailment. But it's a bit fiddly, so we need to go through this slowly. So recall the problem was we're examining ravens 1 to 101. to try and see if they're black. Okay. The problem we had was, if you look in the absence of any evidence, classical inductive logic, or indeed objective Bayesian inductive logic, will attach probability a half to the 101st raven being black, which is fine, but it will also attach probability a half to the 101st raven being black, conditional on the first 100 ravens being black. And this is where the difference between the objective Bayesian approach and the subjective Bayesian approach arises. Because the subjectivist would say, this is a real problem because this conditional probability is a measure of your degree of belief in the 101st raven being black, given evidence the first 100 ravens being black. So subjectivists measure probabilities given the evidence as conditional probabilities, formally as conditional probabilities. So these are ratios of unconditional probabilities. This is rather different to the objectivist approach. The objectivist would say, what we need is to calculate the probability given our evidence of the 101st raven being black, but this isn't necessarily a conditional probability. We've got to apply our three norms of objective Bayesianism to try and work out what this probability is. It may or it may not agree with this conditional probability, and we'll see in this case in particular that it doesn't agree with this conditional probability. So here's a story. The agent grants that the first 100 ravens are black. So that's the evidence. Also is prepared to grant that this wasn't just a biased sample that sought out the only black ravens in the world, that the sample was independent and identically distributed from a classical approach to statistical inference point of view. So suppose you grant that the first 100 ravens are black and this sample wasn't biased. Now we're going to ask a question, which is how strongly would you need to believe a certain proposition about the chance of a raven being black? So this is the chance that a raven is black, or if you like, the frequency of ravens being black. Suppose this is greater than or equal to x. How strongly would you need to believe this proposition in order to grant it? Now, classical statisticians will say they'll choose a level at which to infer a statement like this. So maybe the 99% level or something like that. Bayesians wouldn't talk about it in those terms. The Bayesian would say, well, this is a decision problem, much like any other decision problem, like the one I showed you at the beginning of this talk. So you'd build a decision table for this decision. The decision is whether or not to grant a certain proposition is true, whether or not to infer it. And if your degree of belief in that proposition is above some threshold, so we had, in our decision table earlier, we had the probability of recurrence needs to be greater than or equal to 2/3. If your degree of belief in this proposition is above some threshold, then you'll go on and to grant this proposition. So suppose, for the sake of the story, that the threshold is 0.99. Suppose you'd need to believe this statement to degree 0.99 in order to grant it. Now, our sample and sampling assumptions tell us some facts about the physical probability of ravens being black. If you apply classical statistics, in particular confidence interval methods, you get some facts about these statistical probabilities. And what classical statistics says is if you want the probability, the frequency of samples to be within some interval of the true frequency of a raven being black, if you want that to equal a certain number, we can tell you how wide to make your confidence interval. We can give you delta. So in particular, if you want 99% of samples to have a sample frequency that is within delta of the frequency of a raven being black, so that's the physical probability of a raven being black, we can tell you what delta should be in order to guarantee that 99% of samples will be within yield sample frequencies within that interval. So classical statistics gives you statements like this, statements about the chances. The Bayesian thinks, oh well, that's a chance statement, I should calibrate to that, so apply the calibration norm. And I should believe, so this is now my belief function, I should believe to degree 0.99 that the physical probability of a raven being black is within delta of my sample frequency, which was 1. So I observed 100 ravens, found them all to be black, sample frequency of 1. So the Bayesian has applied the calibration norm here. But hang on, we said that 0.99 was the level above which you would grant the proposition that the probability of a raven being black takes a certain value. That's what we said up here. So we should grant this as well. Then we apply the calibration norm again. This is a new item of chance information. We should believe that the 101st raven will be black, or any unobserved raven will be black, to degree at least 1 minus delta here. So we've applied the calibration norm twice. Equivocation norm says, well, be as equivocal as possible. So don't adopt the extreme degree of belief 1, for example, but go nearer the 1 minus delta end for your degree of belief. And so the objective Bayesian would say probability 1 minus delta attaches to the 101st raven being black, given everything else you grant. So learning from experience does come to be possible here. You're attaching a probability near 1 to the 101st raven being black. The point to note about the objective Bayesian approach is the crucial role that statistical theory is playing. So you're really applying classical confidence interval methods here in order to attach a probability to a conclusion. Carnap wouldn't like this at all, because Carnap wanted inductive logic to underpin statistics, not the other way round. So this wouldn't be palatable to Carnap. But I think it does solve the problem that besets inductive logic, which is this trying to capture two concepts at once, inductive entailment and logical entailment. So inductive entailment is being captured by statistical theory and the calibration norm here, which says that you should calibrate to chances. Logical entailment is essentially being captured by the equivocation norm, which says you should give each line of the truth table that's compatible with your premises the same probability. So if you adopt the full package, the objective Bayesian package, then arguably you can reconcile these conflicting desiderata, inductive entailment and classical entailment. This was a bit painful going through this long chain of reasoning, but it's arguably something that we do fairly intuitively when we reason in practical everyday life. We don't obviously calculate confidence intervals and so on, but we do calibrate to our to information about chances that's available from in our evidence. So let's go back to the opening example. Here, the objective Bayesian would attach. So these are the probabilities that have maximum entropy subject to these constraints holding. these constraints holding. And probability 0.5828 attaches to the conclusion recurrence. Remember, this wasn't high enough to trigger chemotherapy. It had to be greater than 2/3 to trigger chemotherapy. So the objective Bayesian would say you need to give radiotherapy in this case. The patient's individual symptoms do provide some support for recurrence. They do raise the probability, but not by very much, from 0.53 up to 0.58. So not by very much at all. So the point I'm making here is that the objective Bayesian approach to inductive logic can be used to answer these questions in much the same way as classical inductive logic, and to provide the probabilities that you need for decision making. I'll just close very briefly by saying a few words about inference in inductive logic. So there's a general strategy for performing inference in inductive logic. You've got an entailment relation like this. What you want to do is you want to try and represent all the probability functions that are compatible with this information on the left-hand side, and work out what probability they would give to some conclusion proposition psi. Now, the natural way of representing probability functions is using probabilistic networks. So a Bayesian network can be used to represent a single probability function, or a Creedal network can be used to represent a whole set of probability functions. I won't go into detail as to what these networks are, but I'll just show you some pictures in a minute. So the general approach to inference in this sort of inductive logic framework is build a probabilistic network that represents the models of the left-hand side, use that network to calculate the probabilities that would attach to the conclusion, and then the entailment relationship holds if all these probabilities are in the set Y that you're interested in. So the network that you build will depend on the semantics, what counts as a model satisfying the left-hand side. The objective Bayesian approach would suggest you use a Bayesian network that represents the most equivocal probability function that's well calibrated and so on. But other approaches would differ. How you actually do the number crunching to calculate Y, this is independent of the logic. So the semantics gives you the probabilistic network, and then methods independent of the semantics can be used to attach the probability to the conclusion. So here's an example in propositional inductive logic. Got four premises here. You build a Bayesian network by linking variables that occur in the same premise, and then you attach probabilities according to the links in these networks, and that allows you to represent the probability function that has maximum entropy subject to these constraints. And then you use that probability function to attach a probability to the conclusion proposition. What probabilistic networks do is that they achieve a dimension reduction. So I think in this case you'd need to specify 11 probabilities, whereas if you use the truth table method you'd need 32 probabilities. And you can see as the problem grows, the advantage to using probabilistic networks will grow too. Predicate inductive logic, you just do exactly the same sort of thing. You link variables that occur in the atomic propositions that occur in the same or induced by the same constraint, and then that allows you to calculate probabilities that would attach to the conclusion. So 11/15ths attaching to this conclusion. Okay, so the overall message is this. If you want to do decision making, you need inductive logic. If you want to build decision support systems that can help clinicians and so on, you need decision support systems that implement inductive logic. And I mean viable inductive logics, not kind of ad hoc and unjustifiable inductive logics. The problem is that partial entailment, if you like, is an overloaded relation. There are two connotations to partial entailment. There's inductive entailment, learning from experience, and logical entailment, entailment due to logical overlap between propositions. Classical inductive logic can't capture both those notions, but arguably objective Bayesian inductive logic can. Statistical theory is doing the work here with respect to inductive entailment. And probabilistic networks can be used for inference in inductive logic. Whichever inductive logic you prefer, you can use this machinery of probabilistic networks to perform inference. So it's rather different from proof in deductive logic, but still you've got this rather semantics independent method of inference in inductive logic. So the semantics only comes in building the network, not in performing the inference. Okay, well that's it. So any questions? I'd be happy to answer.
Thanks very much, John. Are there any questions or comments? Yes.
So somehow the semantics here seems quite complicated because you need this inductive, statistical reasoning. What is the analog, or is there an analog of proof theory and formal systems, say for the dumb?
Well, people have worked on proof systems for inductive logic, and there are, I mean, depending on the inductive logic, there are a variety of proof systems, and one person to look at is Joseph Halpern's work on reasoning under uncertainty. He has really looked at proof systems for inductive logic in quite a lot of detail. I have to say that the trouble is with inference in classical deductive logic is hard enough. Adding probabilities tends to just confound problems. So rather than applying systems of proof, the emphasis of this talk has been on applying probabilistic networks because they offer a practical means for probabilistic inference. So in the worst case, using probabilistic networks are intractable computationally for large problems, but in typical cases they can they're quite tractable and are used quite widely. So personally, if you're going to look at these sorts of systems for practical decision support, I would go down the direction of probabilistic networks rather than proof.
Are there more questions? Yep.
How does the notion of partial entailment affect truth, the truth of sentences? I mean, you have a notion of partial truth or something like that?
So here, well, again, this would depend on your semantics. So it's possible that you would have a connection between partial entailment and truth, for example, if you had some semantics that incorporated fuzziness or something like that. But here I've just been focusing on probability, and in particular probability as interpreted as rational degree of belief. So there's no strict connection between degree of partial entailment here and degree of truth. Degree of partial entailment here is just the degree to which you should believe a conclusion given the premises. Of course, it may be the case that you should believe the conclusion very strongly given the premises, even though the conclusion turns out to be false for reasons that aren't reflected in the premises, for example.
Just a quick question. So given the focus that in artificial intelligence now we can solve a lot of problems using machine learning, basically, can we use inductive logic to solve problems that are now solved with machine learning, and what is the added value of using this system?
So the added value is this. So the paradigm of machine learning is very good at coping with the situation in which you've got one good quality data set and you want to fit a model to that data that captures the data in that set and use that for inference. Now, typically in the sort of applications I'm talking about, for example, in the cancer applications, we have large numbers of data sets partially overlapping in their variables, some good quality, some poor quality, and so on. And in particular, the data sets that measure the clinical variables, so size of tumour, age of patient, and so on, tend to be different data sets to the ones that measure the biological markers, or only partially overlapping with those data sets. The traditional machine learning paradigm would allow us to fit models to each individual data set, but it struggles with trying to fit a model to the collection of data sets as a whole. The inductive logic approach is well suited to that latter problem, because basically the calibration says you should fit each individual data set, and the equivocation says regarding anything that's not decided by your data, you should be as equivocal as possible. So it can build a model that is calibrated to individual data sets while being equivocal over connections that aren't reflected in the data sets. So it can be viewed as a kind of an extension, if you like, of machine learning to handle situations that aren't naturally covered by the standard approach in machine learning.
Okay, thanks. I'm sorry, I have to stop the nice discussion here. I'd like to thank Jon again for his presentation. And now we have to, those of you who wanted to attend the Puteano session, I suggest they follow me and I'll tell them where to go. We'll meet, for everyone else, before coffee, we'll meet in the main square, in Piazza dei Cavalieri, so that we'll make sure we then go all together to the right place. Thanks very much.